Concepting is design jargon for the process of coming up with the concept, the idea of what your experience is going to be. And in the concepting activity, you're creating a conceptual framework that will guide the rest of the design and build process. This is where you figure out if you should go with augmented reality or virtual reality or something in between. You sketch out a storyboard that shows different scenes and actions your audience undertakes. You also collect and organize visual references to guide the look and the feel of the experience. This is, in essence, the truth or the ground truth of what you're trying to achieve. And it's necessary to get the concept right because you're working in a team of people. So even though it's an evolving thing, it's helpful to have a clear concept that everybody can kind of buy off on or get involved in. Here's an example of a storyboard frame, visual directions for the Heroes project that I premiered at Sundance New Frontier. In the third course, I dedicate a full session on the deconstructing of this project, and we'll touch on concepting. So as part of the concept, you will most likely want to prototype some of the scenes to scale in 3D. And to make anything in 3D, you need to model it. Modeling is the process of defining the geometric structure of a 3D object, then virtually painting it by giving it a material, a surface, as well as describing how light should interact or bounce off of it. Think of it as sculpting. If you want to sculpt something, you would use clay, right? And clay is your object. So the act of sculpting with clay is similar in 3D. We have to work through figuring out what's it going to look like and what is the internal geometry of it, and then also what's the finish to it. And tools frequently used for modeling are in no particular order Maya, Blender, 3D Studio Max, Cinema 4D, Substance Painter, and ZBrush. These are all professional tools that have quite a steep learning curve, though once you're used to the tool, it's very powerful. It's also very common to mix and match the tools, not just a single one. In mixed reality, we're borrowing from the visual effects industry and the gaming industry. These tools were not created for mixed reality. They were created to do the effects that you see in Hollywood movies and TV shows, as well as if you play a game on an Xbox or on a gaming console. So we look at the list of the tools. Some of them are general and some of them are very specific. For example, Substance Painter and ZBrush are more specialized tools that would work together with others. And once you get into this and you start learning more about the tools, you'll find that there's a whole bunch of small tools that fit with the larger tools. And in essence, what you're doing in modeling is you're creating a pipeline of tools that you rig together that connect together to be able to create the models. So with geometry and the look of the object defined, we need to breathe life into it. The animation activities is about making objects behave in a way that matches our intent. For characters, we use animation to breathe life into them. This is what Disney explored in the 30s with the cartoons that he was creating. When we look at what Disney did with animation, Mickey Mouse, early animation, he had the benefit, him and his team had the benefit of working just in 2D and rendering that to a film and playing it back. Animation in mixed reality is trickier than animation for 2D because of our short render times, our real-time render times. We only have 10 milliseconds to make that frame for our audience. And in 2D animation, you can render out all your sequences and composite them, do all this post work, and then the final file is a video that is played back in runtime. But the video playback is dumb. It has no concept of those layers or the motion data or anything that was created for the animation. It's not dynamic, it's pre-rendered. So because there's so little time to render a frame in mixed reality, we need to be efficient in how we do this. And the solution is to focus on creating the motion data and playing that back. Keep the motion data for the runtime engine to use to move the character. So we're not making images of the character moving, we're not making a video, we're making a stream of data that we're capturing that says how the different points of that character need to move over time. Many of the tools used for modeling can also be used for animation: Maya, Blender, Cinema 4D, and 3D Studio Max. I wanted to talk a little bit more about how animation works, as it can be a tricky concept to grasp. In particular, it's good to understand the concept of rigging in physics, which we'll dive into later in the session. A naive approach to animation would store the changing geometry of an object for each frame of playback, kind of like video does. It's the equivalent of a 2D image sequence. But instead of describing the pixels, it's describing all the points of your 3D object as it changes over time. It's a lot of data, especially for complex objects. And the problem, so a complex object, for example, is human skin. Animating human skin, there's a lot of polygons in that. That's a complex object. So the problem with the approach, the naive approach, is that it doesn't scale well. If you have a lot of moving objects on screen, you need to process a lot of data each frame. And it's also hard to composite different animations together to make a frame in runtime. So if I'm walking, it's hard to move my hand separately from the walk routine that I have. So a way to solve this is to calculate the geometry of the object in runtime based on an internal, invisible rig or skeleton, and then animate the rig. You define how the geometry attaches to the rig, and the runtime engine uses that to calculate the geometry in runtime. So instead of animating how my skin deforms over time, I'm going to animate how my bone moves, and then the engine can figure out what to do with my skin. So now you have much less data to process, and you can also choose to blend different animation sequences to create composites. So we'll get back into rigs later in this session. Instead of using rigging, you can also use a rules-based approach to motion. Here you rely on the physics and particle systems involved by the engine. A benefit of the 10 millisecond render loop that I was just talking about is that you can use it to model things in real time. So you can use dynamic modeling to determine how things should behave instead of pre-recording it. Most rendering engines have a physics and particle system that calculate in runtime how an object should behave. So for example, if I would drop a ball in VR, I don't actually need to animate me dropping that. The physics system will use the physics properties it gave the ball to determine how to animate it. So animation in its whole, the activity has a lot of different angles to it and different approaches to it. And that's what I want you to take away from that, is that there's not just one way to animate, there's multiple ways to animate. And when you go from 2D, a lot of the animation tools we're looking at, specifically a lot of the tools that were built for visual effects, were built with the assumption of an hour or a day or how many hours for render times, and we only have 10 milliseconds. So that's one of the challenges as we're using tools and borrowing tools from the visual effects industry in mixed reality. Those tools weren't really made for what we're doing, and you have to think that through. And as you're thinking that through, you have to look at how the gaming industry has evolved those tools, and that they came up with using rigging and dynamic and using physics systems to be able to render this stuff dynamically in real time.